Most prospectors unknowingly discard quartz that could yield visible gold if only they knew what to test. The mistake is understandable. Most auriferous quartz lacks glitter or weight at first glance. It's not the showy, buttery load they expect. Instead, it's riddled with micro-inclusions, iron-stained fractures, and invisible sulfides. And it's these overlooked features that matter most when gold is chemically or structurally bound within the quartz matrix. Walk any old mining trail or erosion-cut ravine and you'll find quartz chunks discarded from century-old digs. They're usually white, gray, or oxidized rust red, and they often lie just meters from historic stamp mill foundations. Why were they left? Because to early miners, limited by pan, pick, and eyesight, they seemed barren. But modern tests tell another story. Fire assays, XRF scans, and roast-based extractions now prove that some of these worthless chunks can yield up to 2.5 grams of gold per ton, especially when linked to pyritic zones. A critical field cue is iron staining, especially red, yellow, or orange halos around quartz veins. These hint at oxidized sulfides, especially pyrite or arsenopyrite, classic hosts of gold in hard rock systems. Even if the gold isn't visible, its presence is often tied to these minerals. If a rock smells faintly sulfuric when struck or shows metallic streaks on a plate, you're likely holding quartz worth testing. Yet even these clues aren't conclusive without further steps. The tragedy and opportunity is that most of this quartz is mistaken for junk. It doesn't shine, it's too light, or it's simply in the wrong place. But roasting changes the equation. When done correctly, roasting oxidizes sulfides, fractures microlocked zones, and softens the matrix so that milling and sluicing can finally recover the hidden metal. That's where overlooked rocks become valuable. It's one of the biggest misconceptions in amateur prospecting, that gold-bearing quartz should sparkle. In truth, many of the richest quartz samples appear dull, fractured, and downright unremarkable. The myth of flashy visible gold has led countless rockhounds to discard exactly the kind of stone that, once roasted and milled, could yield measurable recovery. Begin with luster. Most auriferous quartz presents as milky or chalky white, often with patches of iron staining or a faint waxy sheen. The glassy, transparent quartz many associate with gemstones is rarely the target here. Instead, you're looking for quartz that shows disruption, signs that mineralized fluids once surged through it, depositing sulfides and trace metals. Look for rusty coatings, thin black films, or even subtle green-gray smudges where chlorite or other alteration minerals have crept in. Next is habit, the structural form of the quartz. Gold-bearing quartz often occurs in veinlets or stringers, not large geodes or crystals. These veins are typically jagged and inconsistent, sometimes less than a centimeter wide, snaking through otherwise stable host rock. If you're seeing angular, crushed-looking quartz fragments around a vein, that brecciation is another clue. It signals tectonic movement, which often coincides with fluid intrusion and metal deposition. Weight in hand is deceiving. A piece of quartz with iron-rich sulfides might feel heavier than it looks, but don't rely on heft alone. That same stone could also be riddled with cavities or filled with non-gold-bearing minerals like galena or sphalerite. The real indicator is the density and distribution of mineralization. Use a loupe to inspect surfaces. Submetallic flecks of pyrite, fine acicular needle-like, inclusions, or vuggy pockets can all suggest deeper potential. Perhaps the most critical trait is association. Gold rarely travels alone. If your quartz is adjacent to greenstone belts, shear zones, or contact metamorphic zones between granitic and mafic rocks, your odds improve dramatically. Likewise, samples near documented placer deposits, particularly upstream, are worth closer examination. Even float quartz, dislodged and moved by erosion, may retain enough of its source mineral signature to warrant testing. Quartz is one of the most common minerals on Earth, but only a fraction forms in the kinds of geologic environments where gold gets deposited. That's why the surrounding context matters more than the rock's appearance. To understand whether a quartz vein is worth roasting and processing, you have to read the terrain beneath it. Start with hydrothermal systems. These are ancient fluid channels, deep underground pathways where superheated, mineral-rich water once flowed. As the pressure and temperature dropped, those fluids deposited minerals in the cracks and cavities they passed through. Gold commonly rides with these hydrothermal pulses, particularly in mid to low sulfidation epithermal systems. If you find quartz that's ribboned, banded, or interlaced with fine sulfides in a region with volcanic or subvolcanic host rocks, you may be standing over one of these systems. Then there are shear zones, crustal faults where massive rock bodies have slid past each other over geologic time. The crushing, fracturing, and grinding action in these zones creates space for quartz veining, and these veins often host sulfide minerals like pyrite, arsenopyrite, and chalcopyrite, all of which can contain or signal gold. These regions often look chaotic in outcrop, fractured rock, manganese-stained surfaces, and erratic quartz pockets. But that structural messiness is the very thing that allowed gold to infiltrate. Another critical context is contact metamorphism, especially where granitic intrusions meet mafic or ultramafic host rock. These thermal boundaries cause chemical changes that liberate and redeposit metals. In such zones, you'll often see garnet, epidote, and hornfels alongside massive quartz lenses. The combination of these minerals with smoky or iron-stained quartz is a strong tell for gold potential, particularly in orogenic settings. In contrast, quartz found in sedimentary sandstone layers, beach cobbles, or pegmatite dikes with no sulfide trace is usually barren. Likewise, clear or pink quartz crystals from alpine veins or cavities rarely carry gold, no matter how aesthetic they look. Mapping tools, such as historic claim records or government mineral assessment reports, can help narrow your focus. If you're in a zone with documented lode or placer gold, and your quartz samples come from structural or hydrothermal contexts, the odds improve dramatically. Crushing quartz is where most prospecting stops, and that's precisely where hidden value often begins. At first glance, smashing quartz with a sledge or running it through a jaw crusher seems like a complete test. The result: coarse powder or gravel, then a pan or sluice check. If no gold appears, the rock is labeled barren. But this shortcut misses a key fact. Much of the gold in auriferous quartz is locked in sulfides or microfractures that crushing alone doesn't liberate. The problem lies in the scale. Gold particles in hard rock are frequently microscopic, less than 100 microns, embedded within sulfide grains like pyrite or even within quartz itself. Standard crushing might reduce the rock to a few millimeters or smaller, but it doesn't break the chemical bonds or microencasements holding the gold. In fact, partial crushing can compact sulfide particles around gold, sealing it tighter rather than releasing it. Even with finer milling, say, to 100 mesh, tilde 150 microns, you may still be chasing shadows if the sulfide matrix remains intact. That's especially true for refractory ores, where gold is chemically bonded or occluded within iron sulfide structures. In these cases, visible gold is rare, and physical separation methods like gravity or flotation recover very little unless preceded by liberation techniques. This is where roasting enters. Roasting doesn't crush the rock, it changes it. By heating the sample to between 500 and 700 degrees C, sulfides oxidize into iron oxides, typically hematite. Sulfur is driven off as gas, and the rock's structure becomes more porous and brittle. That thermal stress fractures previously intact zones, allowing finer grind and easier separation downstream. In essence, roasting unlocks both mechanical and chemical barriers to recovery. Field tests show striking differences. A quartz ore that pans empty post-crush can, after proper roast and remilling, yield free-milling gold on a second pass. Some assays show recovery jumping from 20% to 70% after roasting, depending on sulfide content. That's a tripling of yield without adding chemicals, just heat and patience. The real alchemy of hard rock prospecting doesn't happen with a hammer, it happens in the fire. Roasting transforms stubborn quartz ore into a material that can finally give up its hidden gold. The mechanism isn't mystical, but it is chemical and structural. And if you understand what roasting actually does to the rock, you'll see why it's the key to liberating subvisible gold trapped in sulfides and microfractures. Start with sulfide oxidation. Gold often occurs alongside iron sulfide minerals like pyrite, Fe(S2), and arsenopyrite, Fe(S). In their raw state, these minerals protect microscopic gold inclusions from mechanical release. Crushing may expose some surface particles, but the gold bound within those sulfide grains stays locked. Roasting changes that by applying sustained heat, typically between 500 degrees C and 700 degrees C. At these temperatures, sulfur is driven off as sulfur dioxide SO2, and the sulfides oxidize into hematite, Fe2O3, or other iron oxides. This not only breaks the chemical bonds, but creates a porous, brittle residue that releases trapped gold during post-roast milling. Thermal shock is the second benefit. Quartz is notoriously tough, but it doesn't handle sudden temperature shifts well, especially when intermixed with other minerals that expand at different rates. Roasting creates microfractures throughout the quartz matrix. These cracks increase the surface area for subsequent crushing and make the rock more friable. Even if gold wasn't locked in sulfides, this fracturing often exposes small pockets and inclusions missed during initial crushing. Color change provides visual confirmation. A successful roast turns pyrite-rich ore from metallic bronze or black to a rusty red or deep ochre hue. This color shift reflects iron oxidation and structural breakdown. If the sample turns light gray or white without significant red tones, roasting may have been incomplete or the temperature too low. If it turns glassy or slag-like, the temperature was too high, possibly fusing values into an unrecoverable mass. Importantly, roasting is not smelting. It does not melt gold or extract it, it simply prepares the ore for easier release. That distinction matters, especially when choosing your setup. Roasting must be oxidizing, allowing airflow, not reducing or sealed, to ensure proper sulfide breakdown. A sealed burn may produce dangerous arsenic fumes or leave gold still chemically locked. Not all quartz is created equal, and not all of it responds to roasting in a way that frees gold. Selecting the right rock before you commit to fire is both a safety measure and an efficiency gain. Roasting unsuitable material not only wastes fuel and time, but may release hazardous gases or produce misleading results. The real key is learning to read the subtle traits that signal locked gold and sulfide presence before the heat ever touches stone. The first trait is visible oxidation. Quartz pieces with rusty red, brown, or yellow surface staining, especially along fractures or contact points, are prime candidates. These iron oxides typically result from weathered pyrite or other sulfides and strongly suggest that more is locked inside. In many cases, the oxidized surface is just a thin rind over a darker, denser core, where the unoxidized sulfides, and possibly gold, remain protected. These cores are precisely what roasting can penetrate. Smell is another underused diagnostic. If a freshly broken piece of quartz releases a faint scent of sulfur or has a slightly metallic odor, you're likely dealing with pyrite, chalcopyrite, or arsenopyrite inclusions. This olfactory clue fades quickly once the rock is exposed to air, so breaking and sniffing a few pieces on site can offer quick insight before you commit them to the crush and roast process. Magnetism offers a third indicator. While gold itself isn't magnetic, pyrite and magnetite often occur alongside gold-bearing pyritic zones. A simple hand magnet dragged over a pile of crushed quartz can pick up fine black particles that, while not gold, confirm the presence of mineral associations worth roasting. If those particles streak dark red or black on a ceramic plate, you're looking at oxidized iron minerals, exactly the pre-roast chemistry that sets up successful recovery. Another vital sign is density combined with fragility. Gold-laced quartz with heavy sulfide content often feels heavier in hand than its size would suggest. If that dense piece also fractures easily along fine lines, it's likely riddled with sulfide veins or microfractures, both ideal for roasting. Contrast that with smooth, clean quartz with no staining or density. It may look more pure, but it's far less likely to contain recoverable gold. Watch for texture. Look closely at the surface under magnification or with a loupe. Dull, granular surfaces or tiny metallic flecks embedded in the matrix are clues. You may not see gold directly, but the metallic matrix, especially brassy cubes or silver-gray needles, often indicates its presence indirectly. Finally, consider provenance. Rocks sourced from historically productive areas, known shear zones, or contact zones with a mining history carry greater odds. Even float quartz found downhill from a known vein can respond well to roasting if it retains its sulfide core. Roasting quartz to extract gold may sound straightforward, but without precautions, it can turn dangerously toxic or even explosive. Many of the minerals that accompany gold in quartz, especially sulfides, contain volatile elements like arsenic, sulfur, and lead. Improper roasting can release these into the air as fumes, risking health, environmental damage, or violation of local laws. The primary hazard is off-gassing. When heated, minerals like arsenopyrite Fe as S release arsenic trioxide as 2O3, a fine, airborne particulate that's both highly toxic and persistent. Even small amounts can be absorbed through the lungs or skin. Roasting indoors, near populated areas, or without a draft-controlled system invites serious risk, not just to the operator but to everyone nearby. The same goes for galena, PBS, which can emit lead oxides and sulfur dioxide when heated past 600 degrees C. Sulfur dioxide, SO2, released by the oxidation of pyrite and other sulfides, is another major concern. While less toxic than arsenic, it's highly irritating to the lungs and eyes and can cause severe respiratory issues in enclosed or windless environments. This gas has a sharp, choking smell similar to burning matches and should never be underestimated. Explosion risk, though rarer, arises when roasting is done in sealed containers or in reducing, oxygen-deprived conditions. If the sulfides don't fully oxidize, volatile compounds can accumulate and ignite unexpectedly. The solution is simple but non-negotiable. Always roast in a well-ventilated, open system where oxygen is plentiful and exhaust gases can escape safely. Material choice also matters. Never use galvanized steel for your roasting container. Zinc fumes are toxic when heated. Similarly, avoid plastic or painted surfaces near the heat source as they can melt or release noxious compounds. Use refractory brick, ceramic, or high-temperature steel designed for fire exposure. Even your fuel choice plays a role. Wood fires are accessible but harder to control precisely, while propane setups can overheat if left unattended. Finally, consider environmental legality. In many jurisdictions, open roasting of mineral ores, even on private land, requires permits due to the potential release of heavy metals or toxic gases. Roasting near waterways or in fire-prone areas without proper containment can result in fines or criminal penalties. Always check local mining and environmental codes before operating any roasting setup. Personal protection is essential. Use a half-face respirator with P100 filters rated for metal fumes, not just dust masks. Safety goggles, heavy gloves, long sleeves, and a fire extinguisher should be part of your standard gear. Roasting isn't inherently dangerous, but it demands respect. A proper roasting setup doesn't need to be expensive or elaborate, but it does need to control three key elements: heat, airflow, and containment. Getting these right ensures that sulfide minerals oxidize fully, gold is liberated effectively, and hazardous gases are safely managed. The goal isn't to melt anything. It's to open the rock structurally and chemically at sustained high temperatures without sealing off oxygen flow. Start with the container. A modified steel drum, ideally a 15 or 30-gallon size, works well as a base. Cut large ventilation ports near the bottom to ensure airflow and install a raised grate or fire brick platform inside to hold your ore above the fuel source. This keeps flames and gases circulating under and around the material. Line the interior with fire brick or refractory cement if you plan extended burns. Unlined drums warp and degrade quickly under repeated thermal stress. For fuel, hardwood or charcoal can suffice in remote setups, but propane offers better temperature control and a cleaner burn. A propane weed torch or turkey fryer burner positioned beneath the drum can reliably reach 500–700 degrees C, the range needed to oxidize most sulfides. Place a removable mesh lid or wire screen over the top to prevent rocks from popping out while allowing gas to escape. Temperature monitoring is crucial. An infrared thermometer with a high range, at least 1000 degrees C, lets you spot check surface temps. For better control, install a thermocouple probe through the side of the drum at ore level. If the internal temperature spikes above 750 degrees C, ease off the flame or lift the lid to dissipate excess heat. Sustained overtemp risks melting components and sintering ore into a fused mass, reducing gold recovery. Ore preparation makes a difference too. Crush your quartz to about a ½ inch or smaller, large enough to avoid dust blow-off, but small enough to roast evenly. Spread the pieces in a single layer for uniform exposure. Avoid packing the drum with too much material. Uneven heating can leave some sulfides unreacted and reduce effectiveness. Set up your roasting station in an open, downwind area with no flammable vegetation or structures nearby. A bare gravel or fire brick pad is ideal. Always keep a Class BC fire extinguisher and a bucket of sand nearby, not water, which reacts violently with molten or overheated metal components. Wear PPE throughout the process: goggles, gloves, long sleeves, and a respirator rated for metal fumes. Roasting times vary by material, but a typical batch takes 2 to 4 hours at consistent heat. You'll see visible color changes as sulfides convert, metallics dull to matte red or yellow ochre, and the rock becomes visibly more friable. When in doubt, err on the side of a slower, longer roast rather than trying to blast heat for quick results. Too cool and the sulfides stay intact. Too hot and you risk fusing gold into a slag that's harder to recover. The sweet spot for roasting quartz lies in a controlled window, typically between 500 degrees C and 700 degrees C, 932 degrees F to 1292 degrees F, where chemical oxidation occurs without melting components or driving gold into a refractory state. Getting the temperature right isn't just technical, it's the fulcrum of success. The process begins with sulfide breakdown. At around 450 degrees C, pyrite Fe2 begins to oxidize, releasing sulfur dioxide and forming iron oxides like hematite Fe2O3. But full conversion typically requires sustained heat above 550 degrees C, held for a minimum of 1.5 to 2 hours, depending on rock size and density. Arsenopyrite, often a gold host, breaks down slightly earlier but releases arsenic compounds in the process, making temperature control and airflow vital. The mistake many make is pushing the heat too high in hopes of speeding up the reaction. Once you pass 750 degrees C, quartz begins to soften, and certain flux-like compounds, like clay or calcite contaminants, can cause partial vitrification. In this glassy state, gold can get trapped instead of liberated. Even worse, exceeding 1000 degrees C risks turning sulfides into silicate slags that resist further crushing or gravity separation. If you see glazed or fused rock after roasting, you've gone too far. Use observable cues as temperature proxies if you lack a thermometer. At proper roasting temperature, sulfide-rich quartz emits a faint sulfuric odor, may crack audibly as internal stress builds, and gradually changes color from metallic gray or brassy gold to deep red, orange, or yellow tones. These visual shifts confirm oxidation is underway. As the roast progresses, odors fade, rocks dull, and a crumbly texture develops. Duration matters just as much. Heating quartz too quickly, especially in propane-fired drums, causes thermal shock that may fracture the exterior while leaving the interior untouched. Instead, bring the temperature up slowly over 30–45 minutes, then hold it steady for at least 2 hours. For particularly dense or large samples, 3–4 hours may be needed. Rotate or stir the material mid-roast if possible, especially in batches over 10 kg, to ensure uniform treatment. Cool down should be gradual. Rapid cooling can reseal microfractures or shock certain minerals into unhelpful forms. Let the drum cool naturally with ventilation open, no water sprays or forced air. Once cool to touch, you'll notice the rock is easier to break, often friable between fingers. That's your signal that the structural work is done. You don't need a lab to tell if your roast was effective. The rock tells the story if you know what to look for. A successful roast transforms quartz not just chemically, but visually and physically. The key is to spot changes that indicate sulfides have fully oxidized, and that gold, if present, is now free or close to it. Start with color. Raw sulfide-rich quartz often carries metallic gray, bronze, or brassy hues from minerals like pyrite, chalcopyrite, or arsenopyrite. After a proper roast, these colors shift dramatically. The once bright sulfides should dull to earthy reds, ochres, or brown-black coatings. Hematite is the most common byproduct, painting the quartz in burnt rust tones. If your rock still shows metallic shine after roasting, sulfide conversion may be incomplete, especially if temperatures were too low or the exposure uneven. Texture is the next cue. Roasted quartz should be visibly more brittle and friable. Even dense pieces will fracture easily under modest pressure, often showing a chalky interior with orange to red streaks. If you can crumble small pieces between gloved fingers, that's a positive sign. You may also notice a dusty residue forming around the sample, oxidized sulfide ash that further confirms conversion. Odor offers another powerful signal. During roasting, sulfurous fumes, sharp and acrid, are common. But once roasting is complete and the rock has cooled, there should be no residual smell. If your samples still emit a sulfuric or metallic odor, especially when cracked, you likely undercooked the core. This is a clue to roast longer or break samples smaller before the next cycle. Magnification reveals even more. Under a 10x loupe or field microscope, freshly roasted rock shows widen microfractures and subtle voids where sulfides have burned out. These voids, often needle-like or granular, are potential escape routes for gold particles during milling. You may also see tiny gold-colored specks in vugs or cracks. These could be liberated gold, but verify with a pin test or streak plate to confirm it's not iron oxide or mica. Magnet response changes, too. Before roasting, pyrite and magnetite-rich samples may react strongly to a hand magnet. After roasting, much of the magnetic pull vanishes or weakens, since oxidation changes the mineral form. A loss of magnetism post-roast suggests that transformation has occurred, especially if combined with color and texture shifts. Roasted quartz isn't just chemically altered, it behaves differently under pressure. Where raw quartz resists force with glass-like toughness, its roasted counterpart fractures easily, producing finer, more consistent particles. This shift is critical because gold recovery efficiency rises exponentially as particle size falls, especially when gold is microscopic or locked in now fractured oxide zones. Start with the first break. If you roasted correctly, even dense ore should crack cleanly with a hammer or jaw crusher. Chunks that previously bounced or shattered into sharp splinters now yield dusty, friable fragments. This alone tells you you're working with a structurally changed material. Break the roasted ore down to roughly 1/4-inch pieces before feeding it into your chosen milling system. A ball mill is ideal, offering consistent grind size down to 100-200 mesh, till to 150-75 microns, which is well within the range needed to release liberated gold from oxidized sulfide zones. Even a hand-cranked pulverizer or heavy-duty blender can achieve this in small batches. The key is not speed but uniformity. Avoid leaving coarse tailings with uncracked gold centers. Sieve your milled material and reprocess any oversized fractions. Listen to the grind. Roasted quartz often grinds softer and faster than raw quartz, thanks to thermal fracturing and oxidation-induced brittleness. Your mill may run quieter or process faster, reducing wear on your equipment. Keep an eye out for dark red or rusty powder. That's your iron oxide residue, a sign of successful sulfide conversion. Interspersed within it may be fine yellowish or metallic specks, potential free gold or native metallic particles released during roast. At this stage, gravity separation becomes much more effective. Use a gold pan, sluice box, or centrifugal concentrator on your milled concentrate. Roasted samples yield higher contrast in the pan. Fine gold stands out better against dark oxide dust than against raw gray quartz fines. Be patient. Gold may be ultra-fine and move slowly during the swirl. Use a magnet to pull black sand and separate non-conductive gold particles more easily. One critical tip: don't overgrind. Pulverizing to the point of flour can cause gold to remain suspended in water or float with surface tension, leading to losses. A sweet spot exists between 100–150 mesh where gold recovery peaks without introducing excessive slimes. If you're losing color during panning, step back the grind slightly. Store your concentrates dry for later testing, smelting, or refining. Label each batch by source and roasting conditions. Tracking recovery per sample helps you refine future processes. And if you haven't yet seen visible gold, don't assume failure. Some values won't appear until sluicing concentrates or running assay tests. Once roasted and milled, quartz ore becomes a different creature altogether, eager to yield gold that was once sealed away. The transition from dry fire to wet wash is where the payoff begins. If roasting was successful and milling reached the optimal grind, sluicing or panning the roasted concentrate can deliver visible, recoverable gold with minimal additional cost. But the dynamics differ from raw ore, and subtle missteps can cost you value. Roasted material has one critical advantage: density contrast. Iron oxides, although still heavy, are less dense than their sulfide precursors. This shifts the gravity curve in your favor. Gold at 19.3 g/cm3 now stands out more clearly against roasted matrix dust ~5, 0 g/cm3 or less, making it easier to isolate through gravity techniques. In raw ore, sulfides often mimic gold's behavior in the pan. Post-roast, that deception fades. Start by wetting your milled concentrate thoroughly before panning. Roasted fines can retain residual dust or hydrophobic coatings, so a drop of dish soap or a wetting agent helps break surface tension and prevent float losses. Use a gentle, swirling motion. Ultrafine gold often rides high in the pan and settles slowly. Watch the transition zone between heavies and tailings. This is where flat or flaky gold tends to collect. Color changes guide your technique. In roasted concentrates, black sands give way to reddish or brownish fines, oxidized residues from pyrite or arsenopyrite. True gold, by contrast, remains bright yellow or metallic, resisting oxidation. If you're seeing brassy flakes or orange-tinted particles, test them. Real gold resists streaking, doesn't shatter under pressure, and remains malleable when flattened. For higher volume, a recirculating sluice setup works well. Use low-profile riffles or miner's moss to trap flat gold. Roasted particles are more uniform, allowing better laminar flow and less clogging than raw, mixed-size gravel. Adjust the water flow until the lighter oxidized rock flushes clean while the heavies settle. Clean your trap zones frequently. Roasted ore tends to produce concentrated but subtle pay. Don't ignore tailings. The first few passes may miss ultrafine particles that need to reconsolidate or separate further. Repan or resluice tailings at least once, especially if visible gold was recovered in the initial pass. If values persist, consider a final upgrade using a finishing pan, Miller table, or even blue bowl concentrator to isolate sub-100 mesh gold. Use a magnet to remove residual magnetite or hematite after panning. While these iron oxides can drag down gold in the sluice, separating them post-process lightens your concentrate and improves gold visibility. However, don't discard magnetic sands immediately. Gold may still be embedded in dense composite grains, especially if roasting was incomplete. Roasting quartz doesn't just unlock gold, it also exposes a gallery of imposters. Chief among them are iron oxides like hematite and magnetite, which can mimic gold's appearance in concentrate but lack its value. These false positives are especially common after roasting, when sulfides oxidize and create fine, dense, metallic-looking grains. If you mistake these for gold, You risk chasing worthless tailings or discarding real pay during cleanout. The most common culprit is hematite, Fe2O3, an oxidation product of pyrite and other iron-rich sulfides. Post-roast, it appears as deep red to black grains with a metallic or submetallic luster. In the pan, it settles heavily, just like gold, and often forms thin flakes that gleam in sunlight. But unlike gold, hematite is brittle. Press it with a steel probe or crush it with pliers. It crumbles or powders, while real gold deforms without breaking. Magnetite Fe3O4 is another master of deception. Though not always present in auriferous quartz, it often shows up when ultramafic host rocks or mafic intrusions are nearby. After roasting, it turns matte black or dark gray and settles heavily in the pan. A quick field magnet test usually gives it away. Magnetite clings immediately. Gold, of course, does not. Yet in roasted samples, even weakly magnetic material can trap gold particles or hide them in clusters. Mica, especially phlogopite and biotite, occasionally survives roasting and appears as flashy, brassy flakes. These float more readily than gold and often flutter across the pan during swirling. While their shape mimics flattened gold, their density is far lower, (2, 8G/cm3 versus gold's 19.3. Swirl gently and observe. If the flake skims the surface or jumps with airflow, it's not gold. You can also perform a streak test. Gold leaves a yellow streak, mica leaves none or a white powder. Another trick is using a pin test. Touch the suspect flake with a needle or knife tip. Real gold resists puncture and will slide or bend. Iron oxides scratch or snap. Under a 10x loop, gold appears smooth, rounded, and lustrous. False positives often show granular textures, sharp edges, or irregular fracture surfaces. Sometimes, false positives come bundled. Roasted ore may contain composite grains, gold flecks within oxidized iron. These can pass basic field tests but still mislead. If you suspect composite particles, save and examine them under magnification. Controlled recrushing of these grains may reveal encapsulated gold. Finally, don't assume color tells the story. Some real gold appears dull or tarnished after exposure to sulfide-rich matrices or high-temperature roasting. Conversely, some oxides retain a warm glow that fools the eye. Always test before discarding. In hard rock gold systems, no indicators are more reliable or more misunderstood than pyrite and arsenopyrite. These iron-rich sulfide minerals are often dismissed as fool's gold. Yet in the context of auriferous quartz, they are among the most consistent carriers of real, recoverable gold. Learning to recognize and interpret their presence is key to predicting which rocks deserve roasting and which to leave behind. Pyrite Fe2, with its brassy luster and cubic habit, is the classic false positive. But in many quartz-hosted deposits, pyrite is not just an associate, it's the host. The gold is rarely on the surface. Instead, it occurs as submicroscopic inclusions within the pyrite grain structure or along microfractures. Fire assays often show that high pyrite samples contain 0.5 to 2 grams of gold per ton, and in exceptional zones, even higher. If the pyrite is coarse, fractured, or oxidized, your odds improve. These traits signal pathways for roasting to liberate trapped gold. Arsenopyrite Fe is even more telling. It appears as silver-gray to steel-colored crystals with a metallic sheen, often with striated or bladed textures. It forms in the same hydrothermal systems as pyrite, but tends to occur in slightly higher temperature zones or more chemically active fractures. Gold often resides not only within arsenopyrite grains, but also at their boundaries, where arsenic content alters the crystal chemistry and creates microtraps for precious metals. Field recognition is subtle but reliable. Strike the rock. Pyrite smells faintly metallic. Arsenopyrite smells distinctly sulfuric with a bitter, almost garlic-like edge due to arsenic. Under a loop, pyrite presents as geometric cubes or multifaceted grains, while arsenopyrite tends to show elongated or wedge-like forms. Both are harder than gold but more brittle. Pressing a pin into either leaves a mark, whereas gold merely dents. Roasting behavior differentiates them further. Pyrite oxidizes readily at (500 degrees C, giving off sulfur dioxide and converting to hematite. Arsenopyrite begins breaking down earlier, around 400 degrees C, but releases arsenic trioxide, a toxic vapor that demands strict ventilation and PPE. Post-roast, pyrite-rich ore turns deep red or orange, while arsenopyrite-bearing rock may show gray to yellowish residue or greenish halos due to secondary minerals like scorodite. A magnetic test can help narrow the diagnosis. Neither pyrite nor arsenopyrite is strongly magnetic, but their oxidation products, especially after roasting, may become weakly magnetic. If you see a color shift but no magnetic response post-roast, it supports a high arsenic or high gold potential zone. Combine that with visible red oxidation and friability, and you're on the right trail. Importantly, the presence of these sulfides should shift your sampling and grid pattern. Follow the fracture lines or veinlets carrying pyrite arsenopyrite, even if the gold isn't yet visible. Document their direction, width, and mineral concentration. In many mining districts, economic veins measure less than 30 cm wide, but follow them far deeper or longer than surface exposure suggests. The presence of pyrite and arsenopyrite doesn't guarantee value, but their absence in auriferous quartz often signals that you're chasing the wrong zone. With their help, you can refine your collection strategy, roast more selectively, and recover more gold from less rock. Carrying tons of ore out of a remote canyon is rarely practical, and in many cases unnecessary. With the right tools and strategy, you can roast and test quartz on site or with minimal setup at home. But this mobility comes with trade-offs in temperature control, environmental risk, and legality. Knowing where to roast and how, without drawing fines or creating hazards, is as crucial as the roast itself. Field roasting is possible but must be approached with discipline. A basic field kit might include a high-temp steel mesh basket, refractory-lined firebox, portable propane torch, and IR thermometer. Quartz is pre-crushed to ~1 inch and loaded in small batches to ensure even heat exposure. Propane torches can bring samples to 600–700 degrees C in under 30 minutes, but maintaining that temperature evenly across a batch outdoors requires wind protection and constant attention. A simple refractory brick wind wall or deep-sided burn chamber helps stabilize the flame and prevents heat loss. Backpack-sized setups can process 2–5 kg of ore per cycle, making them ideal for scouting trips where lab analysis is impractical. Still, they come with key caveats. You must roast in well-ventilated legal areas, never near dry brush, inhabited zones, or water sources. Public land regulations vary by country and jurisdiction. In U.S. BLM or Forest Service lands, open roasting is often prohibited due to fire and emissions risk, even on casual use claims. Always check local restrictions before igniting anything. The home lab approach offers more control and safety. A small propane-fired kiln or repurposed pottery kiln, modified with a vented top and temperature control, can roast several kilograms of ore cleanly and consistently. For tight budgets, a steel brake drum or old barbecue smoker lined with refractory wool can be adapted into a reliable home roaster. Add a digital thermocouple and controlled gas input, and you've built a compact unit capable of holding 600 degrees C+ for hours, enough to oxidize most sulfides completely. Still, residential roasting brings regulatory and safety issues. Arsenic and sulfur off-gassing can pose serious health risks to occupants and neighbors. Vent stacks with scrubbers or fume filters, e.g. activated carbon, are highly recommended, especially for arsenopyrite-rich ore. Some jurisdictions classify this kind of activity as industrial or hazardous if conducted in non-commercial zones. Discreet, responsible operation is essential, not only for your health but for community tolerance. To bridge both worlds, some operators roast at remote private sites or on mining claims with permission. Even a makeshift shelter with brickwork, airflow control, and fire breaks can turn a test site into a low-impact, high-yield lab. But always carry fire suppression tools, wear PPE, and avoid roasting in high wind or fire ban conditions. Mobility extends your range and allows you to test more zones faster, but it also demands restraint. Only roast samples that have passed visual, magnetic, and contextual screening. Carry out all ash and waste. Roasted rock can still leach heavy metals or retain residual toxins. And never roast near streams, caves, or vegetation. Even trace runoff from roasted sulfides can harm local ecosystems. Talk is cheap. Numbers tell the truth. To validate whether roasting truly unlocks gold from quartz, you need assays, laboratory-grade measurements of gold content before and after thermal treatment. These results don't just quantify recovery, they also confirm what your eye and pan can't detect. Submicron gold that evades visual identification, but adds measurable value to your ore. Consider a typical case. Raw quartz sampled from a vein showing iron staining and scattered pyrite. A 5-kilogram batch is crushed to an inch and submitted in 2 parts, one unaltered, one roasted at 650 degrees C for 3 hours. The pre-roast assay might return 0.6 grams of gold per ton, a low but notable reading. After roasting and recrushing to 100 mesh, the same material from the same source can return 2.1 grams per ton, a 250% increase in extractable value. That uplift doesn't come from new gold, it comes from access to what was locked away. Lab analysis confirms why. In pre-roast samples, scanning electron microscopy often reveals gold encapsulated in unoxidized pyrite, arsenopyrite, or quartz fractures sealed by pressure. After roasting, the pyrite matrix converts to friable hematite, and those fractures widen or collapse, releasing previously inaccessible gold. Even samples that look barren post-roast can show higher assay values due to freed ultrafines. Side-by-side pan comparisons echo this. When milled and sluiced identically, roasted ore often yields 2-3 times more visible gold in concentrate. Field test kits, including nitric acid drops and streak plates, confirm the presence of real gold, not just metallic imposters. Magnet sweep tests post-roast also show reduced magnetic residue, indicating sulfide breakdown and cleaner concentrate separation. In high arsenic ores, assays reveal an even sharper contrast. Some arsenopyrite-bearing quartz shows less than 0.5 GT gold in raw form, but after roasting, it tests at 3.5 GT, occasionally higher. That's because arsenopyrite locks gold within crystal boundaries that only thermal decomposition can open. It's no coincidence that many refractory gold ores, ones that defy conventional cyanide leaching, are processed commercially through roasting or autoclaving before any meaningful recovery occurs. These numbers aren't just academic, they shape your strategy. If roasting boosts assay value significantly, it justifies additional investment in equipment, safety gear, and processing. If the uplift is marginal, you've saved yourself the effort of hauling ore for minimal return. Either way, assay data transforms guesswork into decision-making. Collect your own evidence methodically. Label all samples clearly: pre-roast, post-roast, grid location, depth, and collection date. Use certified labs when possible, especially for bulk samples above 5 kg. Even small hobbyist-grade assay services can produce accurate gravimetric or fire assay results within 2-5 days. Every method has its limits, and roasting is no exception. Despite promising visuals, strong oxidization, and even dense sulfide presence, some quartz simply doesn't yield economically recoverable gold. Understanding when roasting stops being effective is crucial to avoid wasting time, fuel, and effort on material that looks good but tests poor. The most common pitfall is low gold tenor in high sulfide rock. It's easy to assume that because a quartz sample is packed with pyrite or arsenopyrite, it must carry gold. But gold content in sulfides is highly variable. Many sulfide-rich zones, especially in distal or barren limbs of hydrothermal systems, contain less than 0.2 grams of gold per ton, even when visually impressive. In these cases, roasting will still oxidize the rock, but the final assay remains uneconomic. Then there are structural traps without mineral content. Some quartz samples show extensive fracturing, iron staining, and friability, all the hallmarks of auriferous ore, but lack actual metal content. These are often the result of physical deformation rather than mineral deposition. Without pyrite, arsenopyrite, or telltale gold hosts, the roast releases nothing. A pan test might yield trace flakes from accidental contamination or upstream float, but lab assays show the truth: trace levels or undetectable gold. Quartz with silica overgrowth is another trap. In some veins, repeated fluid pulses cause quartz to recrystallize over earlier gold-bearing stages, effectively sealing off any recoverable content behind fresh, barren material. Unless your roasting and milling reach those earlier horizons, which may be uneconomical at small scale, you'll recover little or nothing. This overgrowth often appears as unusually clear, colorless quartz with few oxidation streaks. Don't be fooled by its clarity. Even samples that yield modest visible gold post-roast can become uneconomic if milling costs and recovery effort outweigh the return. If you're processing 50 kg of ore for half a gram of gold, roughly $30 USD in value, but spending days of labor, fuel, and equipment where to get it, your net return might be negative. Hobby-scale prospecting accepts that margin, but if your goal is sustainable or saleable yield, these numbers matter. Environmental risk also shifts the balance. Roasting arsenopyrite-rich rock carries legal and health liabilities if done improperly. If your yield is low and your ore high in arsenic, even small-scale roasting may be more hazard than reward. It's better to discard or store such material safely for future processing, if better infrastructure becomes available. To test whether your rock is worth roasting, set benchmarks. If your pre-roast assays return under 0.5 GT and post-roast gains are less than 2x, it's likely uneconomic unless the ore is easy to process. If multiple roasting cycles still produce poor pan recovery or tailings reprocess tests yield no improvement, the source may be depleted or inherently low-grade. Still, failure has value. It teaches you where the system ends and where to focus next. Often, a barren outcrop signals that richer mineralization lies uphill, across a fault, or within a different lithologic contact. Mapping these non-productive zones helps define the structure of productive ones. Once you've roasted, milled, and panned your way to visible gold, the question becomes practical. What now? For small-scale prospectors, recovered gold, especially fine flour or mixed concentrate, exists in a gray zone between personal collection, private trade, and potential commercial value. Each option carries its own trade-offs in purity, legality, effort, and reward. If your recovered gold is coarse, flakes, pickers, or small nuggets, you have the most flexibility. These pieces can be sold as is to collectors, jewelers, or dealers who value natural gold in its raw form. Prices vary by size and form, but well-formed pickers can sell for 5–20% above spot due to their aesthetic and specimen value. Online marketplaces like eBay or specialty auction platforms allow direct sales, though fees and buyer skepticism around authenticity can reduce your margins. Fine gold and concentrates are another story. Flour gold, particles under 100 mesh, rarely fetches premium unless extremely pure. It's also harder to weigh accurately without a calibrated scale and more difficult to sell without refining. The most common route is to accumulate at least 1 ounce, approximately 1 grams before considering a smelter or refiner, who will typically pay 95–98% of spot price, minus assay and processing fees. At smaller weights, expect a bigger cut. Some refiners won't accept less than 5–10 grams and may offer only 70–85% of value for unrefined dust. If your material is mixed with black sands or oxides post-roast, consider it home refining, only if you understand the risks. Methods like nitric acid parting or aqua regia leaching can produce near-pure gold but require chemical handling, waste neutralization, and legal compliance. If improperly done, you risk toxic exposure or environmental violations. Never refine indoors without proper fume handling, and never pour melted gold into water, a common and dangerous mistake. Another option is to sell to local buyers. Coin shops, pawnbrokers, or jewelers may offer quick cash for clean gold, but usually underpay, offering 60–80% of spot, especially if purity isn't documented. Always weigh and test your material beforehand to negotiate confidently. A pocket XRF analyzer or simple acid test kit can help you prove content. For some, holding is the best strategy. Gold remains a hedge asset, and even small personal stockpiles can serve as barter, emergency value, or historical mementos. Labeling recovered gold with source location, date, and method creates traceable provenance, valuable in both collector and academic circles. Some university mineral collections and museums accept well-documented samples, particularly if tied to historical or undermapped mining regions. In some jurisdictions, sale or transport of raw gold from public land may trigger permit issues or reporting requirements. Always check your local regulations, especially on federal or crown land. In many areas, casual use collecting is legal for personal use, but not for resale. Recovered gold from private claims, however, is typically yours to keep and sell freely, provided surface rights are honored. Ultimately, your market path depends on your goals. Are you building a saleable inventory, a collection, or just testing your system? Each use case shapes the best route, from cashing in for equipment upgrades to keeping it in vials as trophies. But the moment gold leaves your pan or smelter, it enters a world full of opportunists, and that's when the next challenge begins. Lowball buyers, mislabeling, and counterfeit risk threaten even small operators. That's where we're headed next, protecting your value from fraud and underpricing. Gold recovery leaves more than tailings behind. It leaves a footprint. Even small-scale roasting of quartz can alter the landscape, introduce chemical residues, or create fire risks if not managed responsibly. The visible gold may be gone, but what remains, ash, oxidized waste, and scarred ground, still speaks to your method and intent. Ethical recovery isn't just about results, it's about stewardship. The most immediate concern is residue management. Roasted quartz loses its sulfide sheen but gains surface oxidation, creating reddish or black powder that, if left unchecked, can leach into soil and water. Especially with arsenopyrite-rich ore, post-roast ash may contain trace arsenic, which can persist for decades in the environment. Never dump roast ash near streams, root zones, or drainage paths. Instead, cool and collect it into sealed containers. Even if values appear exhausted, store it as you would chemical waste, because in many jurisdictions it qualifies as such. When working on public or shared land, visual impact matters. Charred patches, discarded slag, or half-roasted boulders quickly attract attention, and not in a good way. Leave no permanent fire scars. If using a field roaster, place it over a fire brick base or dug-in pad, and clear a minimum 10-foot ring of flammable material. After roasting, collect all residues, douse the site, and scatter sterile, cover rock or soil to mask discoloration. Avoid building permanent structures unless permitted. Roasting also creates airborne risk. Arsenic, sulfur dioxide, and fine particulate matter can travel with the wind, especially in dry conditions. Even low-level exposures can affect wildlife and nearby humans. Always roast downwind of trails, camps, or property boundaries. Use vented lids or spark screens to minimize spread, and never roast in high wind or under fire bands. If others are nearby, notify them in advance, or better yet, postpone your session. Then there's the matter of quartz waste. After roasting and milling, you'll often be left with multiple kilograms of barren, brittle rock. This tailing material may still contain trace heavy metals. Rather than leaving piles behind, consider packing it out or repurposing it safely, e.g., for backfill in non-critical erosion areas or under tarps to harden trails. What you leave behind shapes the next prospector's impression, and possibly the regulations that follow. Even your noise and light signature matters. Remote roasters, especially those using propane or electric elements, can attract unwanted attention. Roasting at night may seem discreet, but creates visible flares and noise in otherwise silent zones. If working near protected lands or private properties, limit activity to daylight hours and maintain a low profile. A single complaint can shut down a promising test site. Finally, practice informal courtesy rules that protect future access. Don't roast near known heritage sites, wildlife dens, or trailheads. If working near an existing claim, always secure permission. Roasting ore adjacent to another's claim, even float material, can cross legal lines in many regions. Respect signage, boundaries, and fair use customs. Ethical behavior now protects your ability and others to explore and recover later. In the end, roasting quartz for gold is more than a method, it's a contract with the land. Each test, each flame leaves a signature. Whether you're chasing value, science, or just curiosity, do it in a way that adds clarity, not conflict. The journey from quartz to gold isn't just about fire, it's about focus. Roasting is a powerful tool, but only when applied with the right rock in the right context with the right intent. After dozens of steps, tests, and trials, what remains isn't just a bit of gold, it's a roadmap. One that separates wasted effort from lasting skill. These final lessons sharpen that map into a field-ready compass for any serious rockhound. First, the rock must earn the roast. Don't default to heating every piece of quartz that looks interesting. Use pre-screening, visual staining, sulfide presence, density in hand, magnetic hints, and geologic context. The strongest candidates often look the least glamorous. Dirty, fractured, iron-smeared chunks pulled from structural veins or weathered contact zones. Clear quartz, vuggy geodes, or float with no mineral associations are rarely worth the fire. Second, roasting is about liberation, not transformation. Gold isn't created, it's revealed. If it's not already in the rock, no amount of heat will make it appear. Roasting opens access to what's locked, especially in pyrite, arsenopyrite, and fine fracture fills. But the temperature must be controlled, the duration sufficient, and the oxygen flow constant. Overshoot and you fuse or vaporize value. Undershoot and the sulfides remain intact. Third, control is everything. From your flame to your tools to your records, what you don't measure will mislead you. Track each batch by source, roast time, and temperature. Use thermometers, sieves, and repeatable pan techniques. The difference between success and failure often lies in an unrecorded variable. Consistency builds confidence and prevents false conclusions. Fourth, visible gold is a bonus, not the benchmark. Roasted ore rarely yields chunky nuggets. Instead, it reveals fine particles, thin flakes, and liberated flour, recoverable only by patient sluicing and careful panning. If your recovery rate rises after roasting, even without visible gold, you're succeeding. Trust the assay more than the pan glitter. Fifth, the gold isn't the only outcome. A successful roasting operation leaves behind knowledge, where to return, what zones carry value, which indicators matter. That intel is often more valuable than a single gram of metal. Mapping your finds, documenting assays, and comparing before and after recoveries turns casual collecting into cumulative insight. Finally, ethics aren't optional. Roasting affects more than rock. Done irresponsibly, it damages ecosystems, sparks fires, or sours access for others. Done right, it adds clarity to the land, value to discarded ore, and wisdom to those who pass through. The goal isn't just recovery, it's legacy. Leave a site cleaner than you found it, your samples better understood than when collected, and your records detailed enough to teach the next person. Roasting quartz for gold is a high-effort, high-skill endeavor. But for those willing to learn, observe, and act with precision, it unlocks value most never see. Not because it's hidden, but because it's misunderstood. Now you're equipped to find it, free it, and finish strong.